Thanks a lot, Henrik, and thanks to the organizers of this very interesting conference. I think we have a very broad audience, and I'm learning a lot from all the talks. Hopefully, you'll also learn a little bit from mine. So since there's many people from many different fields, I chose to give a kind of a broad talk. So I apologize to the experts. I probably won't say anything new for the people who have been following this program, but for the rest, I will try to summarize what we've been doing, the people that usually work in calculating and scattering amplitudes, trying to help with this problem, and also what is the outlook of these methods. And so basically what I will try to answer is this question that we asked ourselves a few years ago when we saw the first detection of gravitational waves at LIGO is, can particle theorists such as ourselves help in the effort of this kind of experimental program and the theory that is associated to it? And hopefully I'll convince you that we have something to say. And of course, what do I mean by that? This is what the data looks like. And we've heard today an interesting talk about how in order to go from this to these beautiful detections, we rely on this matching to these waveform templates that are created. So there's these banks of templates for different masses, eccentricities, spins, you name it. And then so we rely on kind of accurate theoretical predictions of these waveforms, which after taking into account the sensitivity of the detector at different frequencies, we kind of match against the data for detection and for parameter estimation, et cetera, et cetera. Okay, so the goal is to help in generating these waveforms. And there's several phases of this merger, as we all know, and they have already been discussed here. And okay, so there's the in spiral where the two bodies are far away from each other and moving slowly and slowly accelerating while they radiate. Then there's a merger phase, which is kind of very non-perturbative, and then there's a ring down. And I think this in spiral phase, the first and longest part of the binary in spiral and merger is a phase which is amenable to perturbative methods, such as the one we use in particle physics and quantum field theory, et cetera. And that's where we will try to help. So let me tell you how we're going to do this. And the current path to analytical waveform looks something like this. So there's input from many places. So for the in spiral phase, there's two of the key inputs are two-body Hamiltonian, which describes the conservative interactions between the two compact objects, whatever they are. So this is going to be a two-body potential that will depend on many things, like these tidal deformabilities we heard, will encode the finite size features of the objects, and of course the kind of corrections to Newton's potential from GR. And apart from that, there are the fluxes of energy and angular momentum, or equivalently the radiation reaction forces, which describe the loss of energy and angular momentum to infinity via gravitational waves. So these two things are computed in perturbation theory in this in spiral phase, in perturbation theory that I'll describe in a second. And there are two of the ingredients that go into the generation of these waveform models. So there's other inputs from kind of the probe limit or corrections like self-force. There's input from numerical relativity, from rag-hole perturbation theory for the ring-down phase. And so there's input from all of these places to generate these waveform models, such as effective one-body, which Jan has very nicely summarized in his talk. Okay, so our goal is to be helpful for this program. So we'll try to say something about these basic ingredients, these two key ingredients that I described here, which are these two-body potentials or two-body Hamiltonians and the fluxes of energy and angular momentum. And the approach that we follow, because we are particle physicists, we don't like things which are bound. Typically, we like things which are unbound and that scatter. And so if I had to summarize it in a sentence, what our program is about, we're going to solve the scattering problem, where instead of solving the problem of two compact bodies being bound and slowly losing energy by gravitational waves to infinity and merging, we're going to solve the problem of two compact bodies coming in from infinity, interacting gravitationally, and going off to infinity. And in fact, we will solve that problem not in a classical theory, but in a quantum theory that will allow us to use some of the kind of powerful tools that we have that have been developed for collider physics to do these calculations. And then we'll try to take the classical limit to make connection to the classical dynamics that we are interested in for gravitational wave observatory. Okay, and so basically we will be able to compute these basic ingredients from the scattering problem. So these ingredients don't depend on the dynamics that you're describing. They're just things that describe the dynamics itself, and you can solve them with different initial conditions, and then they'll tell you about the bound problem or the unbound problem. Okay, and so there's other methods for computing these objects in the post-Newtonian setup. There's this tutti frutti or NRGR, also using methods from quantum field theory. There's other methods in the post-Minkowskian setup, also using wordline theories, such as this post-Minkowskian EFT. I won't be talking about those. I think there's going to be talks about those later in the conference, but many of the things I will say are actually techniques which are complementary and that were developed in the context of scattering amplitudes, and now they're being used also in these other approaches, at least in some of them. And so if you have questions about those, you should ask the people who speak about them. Okay, so traditionally, the perturbation theory for this in-spiral phase has been approached in this post-Newtonian expansion. So this is an expansion for a virialized system where kind of the velocities of the objects relative to the speed of light are small, and they're comparable to the kind of ratio of the Schwarzschild radius of the system to the separation. So these are things which are far away from each other and bound, so they're slowly moving. And so there's effectively one small parameter, which is v squared over c squared, or gm over r, at least in the conservative sector. Okay, and then whatever quantity that you compute is going to have an expansion in these parameters. And for instance, the potential, this two-body potential, and the post-Newtonian expansion is an expansion that proceeds in this vertical direction here. So the leading order, say, of the potential is the Newton's potential, which it has been known for a while. Then the leading correction to this is this Einstein-Full-Hoffmann, like first post-Newtonian correction to Newton, which includes both a term of order g v squared and a static term of order g squared. And since then, there's been kind of steady progress over the last century in computing all of these post-Newtonian corrections. And the state of the art, which is completely known, is 4pn. There's some work and some discussion being had about what 5pn looks like. So there's computations, and these will be resolved very soon, I think. And there's also very amazing progress at the 6th post-Newtonian order, which I didn't plot here by many people. So yeah, so this is what's natural for the bound problem, and one of the goals could be to compute these post-Newtonian corrections, which are going to be relevant to generate these waveforms. Now, the scattering problem suggests an alternative approach, which is to approach this in a horizontal direction. So because we have an unbound system, then the velocities of the system, they're not virialized, so they can go, the objects can go as far as they want. And then it's more natural to compute a fixed order in g Newton or gm over r, and to all orders in velocity. Okay, so this is the usual post-Minkowskian expansion. And every term in the post-Minkowskian expansion encodes an infinite number of terms, of post-Newtonian terms at a fixed order in g Newton and different orders in velocity. So any calculation that we do will inform future post-Newtonian calculations, and has already done so. And also notice that for a given PM order, say 2PM, which is order g squared, the only piece from the 2pn which is missing is the static piece. Okay, so 2PM doesn't encode the full 2pn dynamics, but it encodes it up to kind of a static contribution, which is kind of a velocity independent part of the potential at one higher order in g Newton. Okay, so this is more natural to approach from the scattering perspective, and that's what we do. And so the two main results that have come out of the program. So first I will tell you what we've done, and then I will have some comments about how we did it, and then the challenges going forward. And so these are the two key results that have come out in the last couple of years. So the first one in 2019 was the 3pm correction to the Newtonian potential. In a particular gauge called isotropic gauge, you can do a change of canonical transformation to your favorite coordinates. And then last year, we computed the 4pm potential, which is the order g to the 4th potential, and which has also been reproduced by another group using these wordline methods. Okay, so let me show you what these things look like, just so that you get an idea. Okay, so the potential is an expansion in gm over r. So from now on, c is going to equal 1, unless I print it explicitly in a slide. So these C's here are some coefficients that depend on the velocity of the two objects. And schematically, they look like a function of the masses and the energies times this m tilde object, which I call it that because it will be related to the scattering amplitude in some form. And these things are quite simple. So for instance, the leading order is just 2 gamma squared minus 1, where gamma is the usual Lorentz factor, the usual relativistic factor. Okay, and this encodes a complete series of post-Newtonian terms. At the next order, at order g squared, is 5 gamma squared minus 1. And then starting at order g cubed, there's some interesting transcendental function that appears in the result, which is some Arcosh. And these f's here, they're just some function of this gamma factor, some polynomial or some rational function. Okay. Okay, so this doesn't look too complicated. At the next order, which is the computation that we did last year, the result looks much more complicated. And this is just so you get an idea of what it looks like. So it has different pieces. Some of them are purely rational, which encode the probe limit, this M4P. There's also some logarithm, which is related to the energy loss. I won't describe that in detail. And then there's some transcendental contributions, things that involve complete elliptic integrals, and also other kind of polylogarithms and logarithms. And, so it's kind of an intricate analytical function of the velocity, which we can check in many limits. We can compare against the PN literature. We can check that it works in the probe limit. And this also includes these conservative radiation reaction effects that were described in Stefan's talk. And I will say something more about those, okay? So this is just so that you get an idea of what we can do. And you can ask the question, are these things useful? And I think Jan already hinted at the answer to this question in his talk towards the end. And so here are some plots that were produced by Bonanno's group, where they took these 4 p.m. Hamiltonians, which, as I'll explain later, one has to use them with care because they were derived for hyperbolic motion, and there's some subtlety, but and one can see that indeed, so the dashed line here is numerical GR, and here this is actually the scattering angle for different values of the impact parameter, and one can see that there's an improvement relative to the previous order. This is before fitting it through any kind of effective one-body machinery. Of course, the agreement to numerical GR gets much better after using the effective one-body resonations. And similarly, this is the binding energy, again, compared to numerical GR. And this was for equal masses. This is for kind of mass ratio of order 10. And we can see that actually, like the 4 p.m. is very, very close to the actual result from numerical GR. Okay, and in the bottom part of the plot, there's a relative difference also supplemented by other additional PN terms which are known. Okay, so you can look at their paper. They have kind of an exhaustive analysis of how well these Hamiltonians do before and after EOB and for different mass ratios. And I think the conclusion, so the authors which are in the audience can correct me if I'm wrong, but the conclusion is at least for the circular orbits with comparable masses, this essentially agrees with the 4 p.m. Hamiltonian, and it doesn't provide a significant improvement, but one can see a significant improvement for the hyperbolic motions, which hints at what Jan said, that for highly eccentric orbits, these post-Minkowskian corrections will become more and more relevant. Okay. So yeah, we can talk more about this later. So let me move on to something else that we can compute. So I told you that the other ingredient for the dynamics are the fluxes, and something that can be computed also using methods from scattering amplitudes. Again, I won't tell you yet how we do this. I will tell you about it later, but are the total energy laws or total angular momentum laws in a scattering process. And so again, this is just so that you see what they look like as a function of gamma, of the 4 velocities. All these R's, again, are rational functions of the gamma factor. So the angular momentum laws also was computed in 2020. The leading order was known for many, many years, since the 70s by Kovacs and Thorne, but this encodes all orders in velocity for the G cubed, which is the leading energy loss. And more recently, there's been several computations starting with Amor using purely classical methods, and also by other people in the audience, and also upcoming work of the angular momentum loss in the scattering. And So note there's a curiosity that the energy loss starts at 1 order higher that compared to the angular momentum loss, and this is related to the fact that this is carried away by soft gravitons, or it has something to do with a memory effect, which is kind of something very interesting, which maybe Carlo will tell us more about that. I'm not sure, but he's written very interesting papers on this. Okay, so using this calculation, so this is the total energy loss in the scattering. One can bootstrap the instantaneous losses, which are the other ingredient for the dynamics. And I think we'll hear more about that later in this conference. Okay, so this is the status of these calculations. We can compute the basic ingredients for the conservative dynamics, either by computing these potentials or by computing these total integrated fluxes. So I think we can put a check mark here that we understand how to provide some of these basic ingredients. Of course, there are subtleties that come in at high orders and already at the orders that we've computed. But now let me tell you how we've done these calculations. But I will pause first for questions, if there's a quick question. All right. Okay, so let me tell you what the strategy is to use tools from effective field theory, scattering amplitudes, and using our approach, we also use the double copy and unitarity, which are ideas in quantum field theory scattering amplitudes. So what kind of ideas from effective field theory we're using? Well, we are going to model these compact objects as a point particle, which is created by some quantum field. And this might seem like an overcomplication, but we'll see that we can actually take the classical limit pretty early in the calculation and very efficiently, so that this won't be much of a loss. And that means that we're going to start with kind of Einstein-Hilbert Lagrangian coupled minimally to some particle. And if we want to include other kinds of effects, we can also do it within the context of these effective theories. So for instance, one can include finite size effects and tidal effects by adding non-minimal interactions of these fields to gravity. So for instance, the love number that we heard about, these tidal deformabilities today, they're encoded in some of these higher dimension operators that are going to affect our calculations. Similarly, we can also add modifications of GR. So we also heard about that today. And we can just add those to our theory and compute the corrections to the potentials and the fluxes and whatever observable that you might like. As well as including spinning effects. So there's quite an industry now of people doing calculations using kind of massive higher spin theories in the classical limit, which makes sense, and computing scattering amplitudes and potentials, et cetera, et cetera. Okay, so I said scattering amplitude. So of course, okay, hopefully most people here know what a scattering amplitude is. It's just the probability amplitude for some scattering event to happen. So when things are coming off to infinity in quantum mechanics, they interact, they come out. The absolute value squared will give us the cross section or the probability. And traditionally, this is written as a sum over Hymen diagrams, which can be easier or harder to compute depending on your taste and your power. And each diagram, it's a function of the momenta and the polarizations of the particles. So here I'm denoting kind of the heavy scalars or the heavy particles that would describe the compact object by a thick line, and the thin lines are gravitons, or we're just solving essentially Isaacs equations in perturbation theory. And all, because this is a Hymen diagram, all these particles except for the external ones are off shell. So they don't satisfy the usual Einstein relation between the energy and the momentum and the mass. Okay. So these are off shell particles, and there's some gauge choices that one needs to do when doing these calculations. So these are an ordinary perturbative calculation, but this is the object that we're interested in, and this encodes in a certain way the potential. So a leading order is very easy to do. So let's look at this Hymen diagram, which is the leading Hymen diagram, the only diagram at order G that we can write for the scattering amplitude of two massive scalars interacting gravitationally. And it looks something like that. G times the product of the masses times 2 gamma squared minus 1 over the momentum transfer squared. And the momentum transfer is just the momentum carried by the graviton. Okay. And if we take the Fourier transform of this diagram and we just expand in velocity, we find, of course, Newton's potential and a few post-Newtonian corrections, including the leading kind of Einstein-Hilbert-Hoffman, maybe in a different gauge. But it's clear that these amplitudes encode in some way these nonlinear interactions of gravity. And indeed, one needs to go to higher orders in perturbation theory, and kind of diagrams with loops will encode the nonlinear interactions in gravity. So one loop diagrams will encode g squared interaction, two loop diagrams g cubed. Kind of the state-of-the-art calculation that was done last year is 3 loops, which is g to the 4th. But okay, you might be worried that I'm drawing loops, and most people think that loops are quantum. But actually here there's 3 scales involved in the problem, and we have to see which of those scales encode quantum corrections and which classical. So the 3 scales are the quantum wavelength of whatever particles we are scattering. So we want to have that quantum wavelength to be very small, so that our particles are essentially point-like. Then there's the Schwarzschild radius of the system, and then there's the separation between the 2 bodies, and we want these 3 to be widely separated. Okay, so the first hierarchy encodes classical versus quantum corrections. The second hierarchy just encodes the usual post-Minkowskian expansion. What we are saying that the relative separation between the bodies is much larger than the Schwarzschild radius. Okay, so these are the 2 dimensionless parameters that we have, and they're both small, but kind of the first inequality, powers in Q over M encode quantum corrections, whereas powers in GMQ in the amplitude encode just the nonlinearities of gravity, or the post-Minkowskian corrections. Okay, so the general relativistic corrections, the kind of the classical amplitude has an expansion in Gm times Q, some power of that depending on which order, and we are trying to find the pieces in the amplitude that go like power of Gm times Q, and those encode these classical interactions. So in which way? So there's a very easy way to connect the amplitude directly to something that most people might be familiar with, which is kind of the on-shell action. So we are all familiar with the usual semi-classical approximation in quantum mechanics, where we start with some quantum mechanical transition amplitude, where we ask, what is the probability for particles with these momenta, these positions at this time to propagate from here to those positions at that time? And the question that we ask in amplitude is slightly different, because instead of fixing coordinates and time, we fix momenta and energies. But the semi-classical approximation is also valid. And instead of having the full kind of classical Hamilton-Jacobi function, what we have is some kind of Legendre transform of that, which is just a radial action integral. So one can see very easily that the semi-classical approximation tells you that the amplitude, a leading order in the classical expansion, is the exponential of the semi-classical on-shell action, which, because we have fixed energies and momenta, it's just this radial action integral. Okay, and another way to say it is that this classical action is the same as the log of the amplitude, which is the phase shift if we write it in terms of angular momentum and energies. Okay, so there's a clear relation between an amplitude and just a classical object, which is the on-shell action. So we can solve for the dynamics of the particles, plug them into the action that gives a function that depends on the angular momentum and the energy of the scattering process, and that is this radial action integral, which is just the integral of the radial momentum along the trajectory. Okay, and actually that thing is closely related to observable. So the amplitude is gauge invariant because it's a scattering amplitude, and hence this radial action integral also is gauge invariant, even though you might compute the trajectories in a given gauge, and you write your action in certain coordinates. Once you plug that back in, you should get a function which is gauge invariant. And you can take derivatives of that function with respect to different parameters, such as the angular momentum, the energy, and then you will relate that to different observables. For instance, the derivative with respect to the angular momentum gives directly the scattering angle. And one can think of this as a derivative of the amplitude. Similarly, time delay, there's also a version of the Weiler redshift for scattering, which maybe self-force people are interested in trying to compute. But anyway, let me move on because I'm running out of time. So we also have unitary methods where we kind of build more complicated amplitudes by sawing other amplitudes, where every single leg here satisfies the on-shell condition. And we like this because kind of the systematics is a bit simpler than Hymen diagrams, at least when one works with scattering amplitudes. So let me not say much about that. And the other main tool that we use is this double copy that relates amplitudes in gravity and gauge theory. So at 3 points, it's easy to see that on-shell, the amplitude for 3 gravitons and 3 gluons is related by a square. And there's a more general relation that actually I won't describe in detail, that if we organize gauge amplitudes, Young-Mills amplitudes in a certain form, allow us to square them get gravity amplitudes, and we can do this at tree level and fit it into this unitarity to build loops. Okay, so let me go fast because I want to get to the future. So let me just say that the calculation that we did our g to the fourth includes these tail effects. So our definition of the conservative dynamics is indeed to use this principal value of these time symmetric propagators. And at this order, these tails have to do with the fact that the potential is actually non-local in time. So it's different for bound and unbound orbits. So we have to be careful when trying to use this Hamiltonian for the problem that we actually care about. And part of the problem, like one of the remaining challenges, is to actually relate these two. And okay, let me come back to this later, but this is just to explain how we can compute also the radiative observables using things like measurement functions for cross sections. So we can write every single one of these radiative observables using this informalism in terms of amplitudes and cuts. Okay, so in order to compute that, the real challenge, and this is the real bottleneck for all these calculations, is to do the integrals. And so far, we can use all the machinery from particle physics, things like integration by part identities, so relations, linear relations between integrals that appear that we can list down systematically and solve to go to a basis. We can solve for those integrals by writing differential equations, which for the quantities I described, they're just differential equations in the velocity that take post-Newtonian data as boundary condition and resum the velocity series. And we can also do this cross-section-like calculations where we have to sum over phase space by using this reverse unitarity trick where we turn delta functions into differences of propagators. So all of this machinery applies. Okay, so no matter if we have ordinary Hymen integrals or cuts of Hymen integrals, we have all of this integration machinery, which actually the same integrals appear in the purely classical Whirling calculations, and we know how to do them. And this is what's going to be the bottleneck for the future. So let me tell you about that, which is where I wanted to get. I think I only have a couple of minutes. And the general philosophy is that we want to proceed one scale at a time. Okay, so an example of this is we're able to compute this energy loss, this momentum loss in the scattering process. And this was given as some sort of weighted phase space integral over the amplitude with an additional particle. Okay, and using these methods from particle physics, we realized that this is just a function of the velocity, so we could compute the integrals easily. That is very different from the waveform. The waveform is a complicated object. At leading order, this has been known since the 870s, but doing these integrals is very hard. And in fact, no one had been able to compute those integrals to get these observables. Okay, so things are easier if one has fewer scales. And in fact, all of the problems that we have solved so far, they're one scale. The only real variable that wasn't trivial was the velocity. Okay, and the frontier for this is g to the fifth, which is 4 loops. And this is equivalent, actually harder than the state-of-the-art calculations in colliders right now, which are things like the angle-dependent cusp anomalous dimension, which was just computed last year, except that we have more propagators. So these are the sort of integrals that they had to compute, and what we have to do now is actually harder. What about 2-scale problems? So this is stepping one step at a time, not going to the full waveform, but things like the power spectrum or the angular dependence of the energy loss. So we like additional delta functions because we can turn them into propagators rather than to do fewer integrals, because doing integrals is complicated. And for instance, this one depends on 2 scales, both the velocity and the frequency in the right units. And we can see from initial explorations that this will likely be elliptic. So this will be a complicated object, and it's important to know this because it's what will tell us what is the local part of these potentials that we computed. So these, the local part of the radial action or the potential is given by an integral over this flux. So if we want to make ultimate contact with the bound problem, we will have to compute this at some point. And then the last thing, of course, is the waveform. And this is really a multi-scale problem. Naively a 5-scale problem, both the velocity and the 4 components of the momentum of the gravitational wave. And only the leading order is known. Okay, and it's been reproduced lately using scattering amplitudes methods, but only the leading order of this is known, and probably we'll hear more about this later. And in fact, in frequency space, this problem is very similar to what people have been doing. So it's very clear that we will be able to go to the next order. So the 1-loop waveform, that's a 5-point 1-loop amplitude everything at one loop is known from colliders, but the state of the art, which is 2-loop 5-point, maybe with one massive leg, which is being done right now at colliders, that's very close to what we will need to calculate to get kind of the 2-loop waveform or the n^below waveform. So we'll get into that terrain very quickly, and probably will need help from people who do QCD calculations. So let me wrap up here since I'm out of time. So hopefully I convince you that some of these words, some of these tools are useful in kind of providing the basic building blocks that go into these waveform models, at least for the spiral phase, and there are concrete technical challenges that have to do with kind of multi-scale integration that will have to be overcome if we want to push the state of the art for things like power spectrum and things like waveforms in the near future. Of course, the ultimate question that I think was already asked in a previous talk is, can we get from this, which is the waveforms from scattering, which presumably contain all the information, to the waveforms from the bound problem, or even can we measure these waveforms for scattering, maybe in the frequency domain? I don't know the answer to that question, but I think we should compute and see what we can learn. So I think with that I will finish and open the discussion.
Thanks for a nice talk. So we have about 10 minutes or so for questions. So maybe start with Stefano, maybe.
Just a quick question. When you say tail, you mean tail or tail and memory?
Say it again.
When you say tail, you mean tail or tail and memory? When you show.
I just mean, well, I mean tail. For us, the definition of tail is you do the integrals with this kind of propagator for the gravitons.
So you have two radiation and one potential.
Yeah. So notice that this middle guy is a 3-point amplitude, so it can only be a conserved. It can only be a conserved quantity. It can only be the mass or the angular momentum. So that's why we call it tail, and why we believe that there cannot be any effect which looks like memory at this order, at least from the point of view of amplitudes, because every diagram that we can draw that has this kind of cap where we have radiation scattering from the potential always has a 3-point vertex, which is essentially the coupling to the mass. Yeah.
Can you go to your in-spiral merger ring down picture? So, yeah. So I think it's more than semantics. I really want to understand. So, right, this implies to me that we should be able to, with the type of methods you're talking about, get all of the blue. But right, the peak. It's not when the horizons touch. It's when a common horizon forms around the object, which isn't the same. But right at that point, you're violating all the assumptions that went into it, and you can maybe get something to behave okay by resumming or whatnot. But
yeah,
and we also know even earlier, right, in the Embry problem, the sequence is converging for a while and then stops converging and runs away. Yeah. So what are your thoughts as far as how far can we really get that blue using the methods that you're talking about?
Yeah, so these are my thoughts. This is, for instance, when you actually compute a quantity which is measurable and gauge invariant, we can test how many orbits before merger we can push these methods to. And okay, you can look at other plots for different mass ratios, but we can see that it's only a few orbits before merger where things go haywire. That's why you need all of these EOB methods, et cetera, to push it to there. So as far as I'm concerned, what we have is an input for these waveform models that push you closer to the merger. But of course, yeah, just the post-Minkowskian or post-Newtonian perturbation theory breaks down much earlier than that. So if you were just doing perturbation theory, that's where you would stop trusting your expansions.
Last question here.
Thank you, Julio. That was great. Towards the end, when you show the waveforms from the scattering and what you're trying to connect, just out of curiosity, don't you have in the scattering problem also cases where particles coming from infinity, they swirl around a gazillion times and then they scatter away? I mean, wouldn't that be a closer analog? And I don't know. I don't even know how to pose the question correctly, but you see where I'm going.
Yeah, I mean, here you can see, so the difference between all these lines are essentially different impact parameters, and you can see that the waveforms are very different depending on what the impact parameter, and presumably some of these will involve things like that. The one issue is that So okay, so for most of these scattering calculations, if we were able to measure this in experiments, we wouldn't need a waveform model because many of these are like the whole process is within the regime of validity of the perturbative expansion. Those processes that you're describing is when perturbation theory will start breaking down. So that's where you might need some modeling, and indeed that what might be more interesting for connecting to the bound case. So yeah, so unfortunately it's again where we will lose control of our approximations. But yeah, I would like to stress that this calculation of the waveforms, which I think are possible based on what we can do in collider physics, I think those will produce a waveform, period, without any extra like modeling or anything. This will produce actual waveforms yeah.
So maybe a follow-up. So you're saying in colliders, you're either missing some physics of the cases where they're going around, or you use a different techniques to try and capture those.
In colliders,
cases?
we never have this sort of event. So there's a very high energies and things come and scatter and then produce other particles. So there's no sense in which you approximately form a bound state or things like that. There's physics like that, for instance, when people consider kind of dark matter scattering from nuclei, things like that. There's this kind of non-relativistic bound state formation, which is relevant, and people have tried to understand that. So presumably there's also some knowledge to be extracted from the literature for those regimes. But this, when I'm thinking about colliders, I'm thinking about calculations of cross sections of incusity for LHC backgrounds and things like that, and none of that is relevant for that.
Red is on. Okay. Can you go back to the slide with your comparison to numerical relativity? Okay. So on the left, it says conservative. And then there's 3 p.m. with radiation and 3 p.m. without.
So here, there's no radiation, even though...
Yeah, I was looking at the scattering angle particularly.
The scattering angle, yes. Yes. So
then,
also here, yes. So there's the 3 p.m. correction, which is the radiation reaction correction to the angle, which you can barely see, but
I don't see where it is on the plot.
it's just on top of 3 p.m. It's
so the radiation makes no difference. It's tiny.
Yeah, well, it makes a difference because radiation effects actually make. If you don't include radiation, you might think that that it's closer to numerical GR than it actually is.
But
everything
negligibly. I'm sorry, I don't even see the difference between them. You said they're on top of each other?
Yeah, they're on top of each other.
So then it doesn't, doesn't that mean it makes no difference?
Yeah,
visually.
That's right, yeah.
Okay, and that's been calculated, but 4 p.m., just inferring from the plot, the radiation part isn't known? Is that the idea?
So the whole radiation reaction contribution to the angle is not known. There's part which is known. The part which is linear in radiation reaction is known, because there's a relation between that and the energy loss and the angular momentum loss. So the energy loss we computed at the relevant order a while ago, and then recently Shashen and Anish Manohar and others computed the 3 p.m. angular momentum loss, which gave them the linear in radiation reaction correction to the angle. At order g to the fourth, there's also a quadratic in radiation reaction correction to the angle, which is not known. Yeah.
Any further questions? Either here in the room or on Zoom? Maybe there first.
Just a real quick question. Is there an intuitive way to understand why the 2 p.m. curve behaves so differently than the others in the cycles before merger energy plot there?
I mean, it's you mean why it's below or above? It seems to be alternating. I don't understand if there's a fundamental reason for that. But I think experience tells us that every order lands on one side or the other of numerical GR. Yeah, I don't have an understanding of why this is the case. Yeah.
There's a question here.
So if you don't resolve to EOB and just carry your calculations forward, do you think you'll converge there or you'll hit some, I don't know?
Well, I mean, so far we are converging. but of course we're doing perturbation theory, so that could stop at some point. And the only way to know is to compute the next order and to go to a relevant region of the parameter space. Yeah, so this approximation breaks down at some point. And as you compute higher and higher orders, you should be able to get closer, but there's a point in which the series won't just not converge. Yeah, but we are not there yet. So there's still some room for improvement. And even though there's some technical challenges, we believe we can push the state of the art further. Yeah.
Hey, this is Ricardo from Zoom. Can I ask a question?
Sure.
Sorry, I missed part of your talk, but why you cannot have a triple vertex with 3 relative gravitons?
Basically, okay, so the technical reason comes down to this. So the fact that we use this principal value of the propagator, so this is essentially a time symmetric propagator, means that the graviton poles are effectively non-existent. So if we try to localize the energy integration of any loop on a graviton pole, you would get 0 because there's no pole. And that means that actually we need every single matter line to be cut. And if you put these 2 matter lines on shell, then this vertex, it just tells you that this potential couples to a conserved quantity. So it basically localizes the momenta of this graviton to be in the potential region, or of this graviton if you cut here or here. So you can just power count with this rule that this thing essentially gets rid of all of the graviton poles. So you need to localize all the matter poles, put them on shell, and if you do that, then if you have a graviton emission from a 3-point from a 2 on shell matter legs, then that has to be just a mass. Yeah.
Okay. I couldn't see your pointer because I'm looking at the slide on Zoom, but I think I understand your argument. But yeah, my point is that you're killing by hand the memory, basically. I mean, it's not that it's not there, that your formalist doesn't see it.
Well, we are taking this definition of the conservative part. So you could
again, I cannot see your pointer. I mean,
okay, so it's the principal value of the propagator. So
sure, yeah, that's what I'm saying.
That definition, then we can see that there is no memory. There's another reason why we think that there is no nu squared terms, which is that if you just power count in the masses all of the diagrams that we find at order to the 4th in the amplitude, there's no diagram that can generate a nu squared in the amplitude just by power counting of the masses. So that's a different argument why we think that there's at order G 4th there's no nu squared pieces. But yeah, so we can yeah. So there was a discussion about what is the definition of conservative. So here's a definition that we use, which is the definition that other people have used, and we've done a consistent calculation using that definition. Then we can discuss if there is a better definition or a different definition.
No, but I mean, it's not a matter of taste. I mean, do you get the right scattering angle? I mean,
what do you mean the right scattering angle? Like
so a nu square order, there are some consistency condition. Even though it's not known the 2 self-force, there are some.
So we don't get
condition.
any nu squared G to the 4th nu squared piece of the conservative scattering angle. That's our result, just from power counting masses in the amplitude. Even without any detail.
So you cannot.
Yeah.
Okay. Sorry. Maybe I'm hijacking the discussion. By the way, will you be there in May?
I can wait. In early June, I'll be here. In May, probably I won't be here. But
okay.
Yeah, we can discuss offline over Zoom. Yeah.
Okay.
Yeah.
Thank you anyway.
All right, I think with that, we probably should end, but let me just check if there's some urgent comments or anything for Zoom. Let me know. No, I don't hear anything. Nobody shouting. So let's end by thanking Julio and also all the speakers in today.